Ok, bon, les gens continuent de venir, mais je pense qu'on peut entre-temps commencer. Alors, je vais brièvement présenter notre nouveau, enfin, il n'est pas nouveau en fait. Monsieur professeur Malik Maaza, il est à sa deuxième présentation maintenant. Donc, c'est la continuation du premier webinaire qui a été fait il y a, je crois, 20 jours de cela ou là, un mois. En tout cas, c'est le premier webinaire. Vous le retrouvez dans notre page, dans notre channel YouTube. Donc, Professor Malik Maaza is a native of North Africa. Actually, he is native from Algeria. He holds a PhD from the University of Paris 6. He is actually currently the chair of the UNESCO UNISA IT Labs NRF Africa in Nanoscience. He is a joint staff of the University of South Africa and the National Research Foundation of South Africa too. He is a fellow of various academies, including the African Academy of Science, the European Academy of Arts and Science, as well as the National Academy of Science of India, the Islamic Academy of Science, and the Royal Society of Chemistry in London. Professor Malik Maaza has been awarded several awards, among them the African Union in Kwame Nkrumah Award of Excellence in Science and Technology, and the Galileo Galilei Award by the International Commission of Optics, ICO. So again, please remind to maintain your microphone closed, muted. And also for those who want a certification of attendance, so don't forget to ask question in the chat. And also you will have a link that Professor Mahidin Judy just sent it in the chat. So please write your answer or your question in the link, and then you will have your certificate of attendance. So without talking anymore, I will give the chair now to Professor Malik Maaza, that he will be presenting the next presentation, Nanoscience from Knowledge Generation to R&D Translation. So Malik Maaza, it's your turn now.
Program Director and dear Chair, Assalamu alaikum. First of all, allow me, dear senior engineer colleagues, participants, to express my gratitude to the organizers for their kind invitation in associating us within this endeavor. Indeed, the talk of mine today is titled Nanosciences from Knowledge Generation to R&D Translations, and this is given within the framework of the NanoAFNet, which stands for the Nanoscience African Network, and the U2ACN2, which stands for the UNESCO UNISA NRF Africa Chair in Nanosciences and Nanotechnology. Within this, in effect, second talk, I would share with you our activities in terms of fundamental science, but also in terms of applied and patent submission. And all of them are related somehow to the Sustainable Development Goals as per defined by the United Nations. So the outline of my talk today is that first I would go fast on what we have seen the last time, just to share the importance of, or somehow why nanosciences is important, and therefore to give a little summary of the background on the related to nanomaterials or materials at the nanoscale. And then after, I will go through a number of examples whereby we went from purely fundamental science to patenting, to submission of intellectual properties. And you would see that in effect, the bridge in between, or the frontier between the fundamental and the applied is, and in particular patenting, is not as complicated as we might think before. And I will hopefully end by conclusion and foresight. The NanoAfnet, the Nanoscience African Network, for which in effect the previous director of the DGRSDT, Professor Hafid Awraq, was one of the founding members, is a network of excellence of the African Union, and the UNESCO chair is a platform. It's the sole UNESCO chair in the South. And while the UNESCO chair is headquartered and administered at the University of South Africa in Pretoria, the NanoAfnet, the Nanoscience African Network, is administered and headquartered at Itamba Labs, which is the largest national facility of the National Research Foundation of South Africa. And in effect, within the two platforms, we do invite extensive amount of postgrad students, MSc and PhDs from all over the African continent, fully sponsored. The same thing for emerging scientists and senior scientists. And also the same thing applies for them. They are fully sponsored and they do come to carry out their research activities in the field of nanosciences and nanotechnology, either at within the framework of the chair or with the framework of the Nanoscience African Network. Just to give an idea, colleagues, about who has been trained through this program, and many of them came, as you can see, from Burkina Faso to Uganda to Cameroon, South Africa, Egypt, DRC, and so on, going to North Africa, Algeria, and Libya, and Morocco. So, and also we do obey by the SDG 5, sorry, that is the gender equity. So the bulk of our fellows who do come to visit us, who carry out their postgrad studies within the framework of the NanoAfnet or the UNESCO chair, half of them are females and half of them are males, and they are treated equally. And the same applies for the emerging scientists and senior scientists. As far as Algeria is concerned, mainly the scientists or students from the CDTA in Algiers, and the Comena from Algiers and University of Tlemcen are the ones who are with whom we have quite a robust interaction so far. And I hope that this platform organized by the Ministry of Science and Technology and facilitated by Prof. Al-Judi and Prof. Nait Mohammed would allow us to host other fellows from other institutions. And you have this presentation is available. I will send the PDF copy. So you have my contact details, my emails. I am the holder of the UNESCO chair, and also I am the chairman of the NanoAfnet. So you can write to me directly and we take it from there. As I mentioned last time, we have had a chance to go through a presentation just to justify what is special at the nanoscale, why materials at the nanoscale are different from the bulk or from the micron, why? And we went and we justified and we gave more or less the background from where the name of nano came and who stated that in 2020, in 2000 we will be able to come with the nanomaterials and we will be able to manipulate them and make them, fabricate them. And how can I say, we mentioned that the nano is in effect, the nanomaterials were existing in the 4th century. The artists were able to make nanoparticles, and we said that in effect nanomaterials do exist as early as the birth of the living species, and in particular through the magnetostatic bacteria. From that, we wanted to say that if we have a particle which is in the nanometer scale, any material which has a size, one of its sizes less than 100 nanometer is called the nanomaterial. And we said in this case, what happens, first of all, if you take a nanoparticle, a small particle within the size of nanometer, the 3D symmetry is broken because the surface of the atom surface or the surface atoms, they do not see a 3D symmetry. It's broken, and therefore you would understand that there will be surface tension issues and correlations. And also we mentioned that any charge localized inside a nanoparticle will be confined because it has a limited space where it is moving in, and therefore the wave-particle duality applies. La relation de Broglie s'applique énormément dans ce cas-là. And we said also the same for the phononic vibrations. And with the vibrations of atoms, also not only will be having a confinement of charges and therefore a wave particle behavior, but also the atoms, when they vibrate, they would not vibrate like in the bulk, and that would be reflected in what we call phonon confinement. Also, we have mentioned that more important, extremely important, if not pivotal, is the number of atoms on the surface relatively to the atoms which are inside the volume. We said that nanomaterials are, how can I say, have high surface to the volume. The ratio can be as high as 50%, even more in some cases. And therefore, the nanomaterial is extremely very active, very reactive with any, how can I say, within any specific condition. And we have mentioned that in effect, nanomaterials are extremely important in view of their surfaces, not the volume, not the mass. It's their surfaces which is extremely important. Therefore, if we take a cube within the length L and we cut this cube in two, we will create two surfaces. If we could take the two splitted parts, we cut them, we will create another set of surfaces and so on. And if we cut them a different direction, the Z, the X, and the Y, we will create a massive amount of surfaces. And therefore, a cube which has these 6 surfaces would be able to have a very large, huge amount of active surfaces, and therefore the nanomaterial will be very active. In particular, when you take your car, the exhaust car, le tuyau d'échappement, whereby you have a platinum to decompose any NOx and any CO2, or to convert the CO to CO2 and so on, or to decompose any toxic gas to less harmful gas, you use platinum. And well, how can I say, in an exhaust, you would not use micron type of millimetric type particles, but you will be using nanoparticles of. And here in particular, if you take just a typical case, colleagues, if we take 1 kilogram of particles of 1 millimeter cube volume, such as the sugar ones, that this kilogram of sugar will have of 1 millimeter cube size will have the same surface to area than 1 milligram of particles of 1 nanometer cube. And therefore, when you have a material like gold, like platinum, that you use in the exhaust of a car, you would not use millimetric particles of platinum as a catalyst to decompose the harmful gases, but you are obliged to go for smaller ones, so to use a small amount. And we said also the colors of materials is not as in the bulk. In the bulk is fixed, while in the bulk at the nanometric scale, it is tunable. It changes, and you can tune it as much as you wish. Here, for example, gold bar is yellow, but the gold spherical part can be moving from red, from yellow to red, from blue to from brown to blue, And also the same applies for silver or platinum. Not only the size affects, but the shape also. And also from thermodynamic point of view, we have mentioned that melting temperature of a material at the bulk is a fixed, while at the nanometric scale, it does change with its size. And this property, colleagues, is important when it comes to metallurgy and so on, and making alloys. Also, we said from electronic point of view, while a semiconductor has a fixed band gap, when you go to a nanoscale, the band gap can be tuned and it's size dependent. Smaller is the gap, smaller is the size of the nanoparticles, larger is the band gap of the semiconductor, and so on. And this is exactly what is used currently in our cell phones, the colors on our laptops, the colors that you see currently within my flat screen of my laptop are due to this kind of nanoparticles, zinc sulfide and other elements whereby we control the size and not rare earth elements. Also, we said that in effect, in the case of nanomaterials, while the shape of bulk material is defined at the nanoscale, it is not. You can give it the shape that you wish, and you play on the thermodynamic, the condition of growth, and so on, and you will be able to have any shape that you want. And here, in particular, the zinc oxide that we use as a sunscreen when we go to the beach or to the Sahara. And here, the same thing can be made in a form of a nano belt, nano ring, nano sword, nano oriented nanotubes, nano tetrapods, nanosciences, and so on and so on. So, colleagues, what is sure is that nanomaterials at the nanoscale have tunable properties. And by that, by the fact that they have tunable properties, they can be used, or they exhibit a large and diverse multifunctionality. And we said that the nanomaterials, you can find them in a form of nanoparticles or independent nanoparticles with different shapes. Here is spherical, here is cubic, and here is a mix of spherical particles and triangulars. You can have them in a form of nanorods or nanotubes, very long ones. You can have also form nanoribbons. You can have them as multilayers and so on. We have mentioned, colleagues, and I will finish by that in effect, the field of nanosciences was driven mainly by data storage capacity. And how can I say, the community or the computer community wanted, or the scientific community, or the humanity as a whole, just the human being community has decided to embark in storing a large amount of information in a small size. And by such, moving from such basic old standard IBM disks, where you cannot even store one MP3 song, to a 1 terabyte USB, whereby you can store thousands of MP3 songs and thousands of movies. So it is this capability of moving from some megabyte to terabytes in terms of storage is the one who has pushed more or less and encouraged and forced the dynamic towards nanosciences and nanotechnology. And in effect, we mentioned that it was just natural to move towards that, because Mother Nature operates as how can I say, at centimeter level. If you take an ant and that goes to some microns to submicron for a red cell to a nanometer for a DNA. The basal length of a DNA is a nanometer, and therefore it was just normal to move like this from industrial point of view, to move from a millimeter type element to micron to submicron and to the nanometer. So that was just normal. So it's not a revolution, but an evolution by say. So we are at this level somehow. And that, colleagues, closes my reminding or summary somehow of the talk of last time. And colleagues, we have mentioned that in effect, the expenditure in terms of funding, funding in terms of fundamental research in particular, as well as applied research, has been increasing within the years is in a tremendous way. Colleagues, here, these are funding in US dollars million expenditure in the field of nanosciences and nanotechnology by different countries. And in effect, in 2015, the US always was dominating, but in 2015, China took over. China is now the first spender in the field of nanoscience and nanotechnology, followed by Japan, then US. And quite a number of countries in the South also came in. Maybe their expenditure is very low, but they came in. So is Africa, India, and Brazil. And that, colleagues, brings me more or less to the start of some of the application or translation that we have managed to share with you. I took this specifically, colleagues, because we have done it from Africa, but we have done it. And colleagues, if you go to Google Scholar, you will see the citation of the work carried out that I will be sharing with you. You see it yourself. So quality-wise, I think in the field of nanosciences and nanotechnology, Africa is capable. African teams are capable to come in. They do not need a huge expenditure to come in, as in the case of, I can say the US or China and so on, but we can come in easily. So I would like just to share with you, colleagues, some points. As you can see, colleagues, here are the countries, the distribution of patents by countries. As you can see, colleagues, here, nearly among the 10 top countries which are involved in patenting and so on, there is no African country here. And as you can see, it is nearly gray all over the African continent. Yet there are some countries like Kenya, like Egypt, like Morocco, Tunisia, and South Africa, and Nigeria, but they are minute, really they are minute. And it's really important to have a mind shift and to move out from purely knowledge generation to translation. And that is in terms of patents in general, but patents in the field of nanosciences and nanotechnology, as you can see, there is no African country at all among, and I think it's really, that is in 2022. I think it shows us that there is a huge opportunity to come in and to, how can I say, I would like just to single out Saudi Arabia, whereby there's a massive amount of IP and encouragement of R&D translations. So I think here it's an opportunity for us from Africa in particular. And in that regard, colleagues, being a university, the University of South Africa is a university which has been created 150 years ago, and it is the largest university in South Africa. It is the largest university in Africa in terms of number of students. It's about 450,000 fellows from all over the country, from all over the world. And here we, after 150 knowledge generation, I think it is, we have been asked to go more or less, not only to not to neglect the fundamental research, but also to bridge and go for applied and translations. And I would like to share with you some of them, colleagues. And all those that I'm sharing with you are a part of the Sustainable Development Goals and our Vice Chancellor institutional catalytic niche areas. The first one that I would like to share with you, colleagues, is the nanofluids. Sorry, colleagues. Yeah. Are nanofluids. And what is a nanofluid, colleagues? Just before going to a nanofluid, I will use this diagram, which is called Enquist diagram. Enquist is a Swedish scientist who came with this diagram. And within this diagram, simply said, he has classified areas relatively to their CO2 footprint. Simply said, colleagues, all the technologies which in the positive side are technologies or areas for their implementation, they will create a huge amount of CO2. While the ones at the bottom here in the negative side, they're how can I say, to be involved in developing these sectors would allow you to minimize the CO2 footprint. And as you can see, I singled out two ones: fuel efficient vehicles, water heating, fuel efficient commercial vehicles. And in regard of these, colleagues, we embarked in nanofluids. What is a nanofluid? And for such colleagues to understand each other, here is an engine of a car. The engine of a car, it has a piston, a set of pistons, and it uses the fuel to move. There is a combustion chamber to, how can I say, whereby the piston operates, and operating, it generates heat, and this heat is removed by water, and that water comes from the radiator, cooled by a fan, and cooled also through the airflow via the radiator, and that cold water will come closer to the engine, and it will remove a heat, and it takes it as a hot. It takes it and it will cool it again in the radiator through the fan and the airflow. It comes cold and it goes back again, another cycle. It removes the heat and it comes back hot, and it is cooled, and again. Each cycle, at each cycle, colleagues, the water will remove a certain amount of heat. Okay, at each cycle. But unfortunately, water has a low thermoconductivity. That means it does not remove heat easily. Why? Because its heat transfer coefficient is less than 1 watt per meter per Kelvin. As you can see, so is ethylene glycol, so is mineral oil, and these are the ones which are used at heat transfer fluids. While metals and their oxides have far higher thermoconductivity by order of magnitude at a certain extent. Because, how can I say, because how can I say, the heat transfer fluids, inorganic or organic, whatever, or standard ones, all of them have a low thermoconductivity. From thermodynamic point of view, if we could include the nanoparticles of these metals or their oxides in these fluids, thermodynamically speaking, we can enhance the thermoconductivity of these heat transfer fluids, in particular the one that we use classically in any heat exchange system. But these particles of metal or their oxides must be nano, very small, very tiny. Why? Because being nano, they will not settle down. They will still be in a suspension as a colloidal suspension. That's one. And second, the gravitation effect will be overcome by the Brownian motion of these nanoparticles, and therefore, thermodynamically speaking, the thermal conductivity will be at least somewhere here, at least. So you do understand that it's important to put these nanoparticles in a heat transfer fluid, the standard one, to increase their thermal conductivity, and that's exactly what we call as a nanofluid. So a nanofluid consists of nanoparticles of metal or an oxide embedded in a standard host fluid. This is the nanofluid. And in effect, the ones who came with this idea, colleagues, is not less than James Maxwell. All of us know les équations de Maxwell. But they're the same gentleman, James Maxwell, in the 17th, he is the one who came with this idea of nanofluid, because except in his time, they were not able to make nano, but the micron-sized nanoparticles, and therefore the micron-sized particles, the gravitation make them settling. So he was not able to do it. But now we are capable to do it. As I mentioned, colleagues, it was James Maxwell who came with the idea of nanofluid, and colleagues, one way to make them is to put a target in a fluid, being it ethylene glycol, being it water or mineral oil. Imagine whatever you want to do, and you ablate with a laser. You ablate the material in that liquid, in that fluid, and you will end by getting a nanofluid. One nanofluid that we embarked in is graphene carpets, graphene sheets decorated with the silver nanoparticles. Why? Silver has the largest thermal conductivity relatively to other metals. Graphene has the highest thermal conductivity than any carbon, including any carbon compounds, including diamond. That is why we went to this. So we have synthesized by laser ablation graphene and silver nanoparticles. And after what we have done, we have synthesized graphene carpets decorated with the silver nanoparticles, as you can see. And that was made easily. And here, colleagues, sorry, by the way, I really do apologize. By the way, colleagues, the fluid that we have used, here is what we call ethylene glycol. Ethylene glycol is that product, that liquid, which is, it depends on the country where you are. It can have a pink color, blue color, or green color. C'est le antifreezer. Well, we have used that one as a liquid, and therefore, as you can see, if you measure the ethylene glycol thermal conductivity is nearly 0.33, okay, watt per meter per Kelvin. And when you take the graphene nanoparticles, covered with the silver, coated with silver nanoparticles, as you can see, the thermal conductivity enhancement is huge. Colleagues, maybe for us as fellows who are not expert in the field, we might think that this is not high. Non. Il faut pas être erroné. This enhancement is huge. Il est très grand, cette augmentation de la conductivité thermique. C'est énorme. C'est énorme. It's an increase of 33%, and this is huge. That means, how can I say, if you mix this with water, for example, what you will have at each cycle, whenever you, sorry, colleagues, I come back to this one, colleagues. If you use this ethylene glycol or you do the same thing in water, you would experience the same thing. And therefore, if you use instead of water, you use this nanofluid, at each time that it goes to the piston here, to the engine, it will remove high amount of heat. And therefore, at each cycle, it will remove a huge amount of heat at each cycle. And therefore, the engine will be under less thermal duress, less thermal stress, and you will be consuming less fuel, and therefore you will be emitting less NOxes and less toxic gases, and therefore your CO2 footprint is low. And colleagues, in effect, this work has been probably patented by Turia Khamlish and myself, and she was a student, PhD student, and the same thing for other fellows who came with. And as you can, colleagues, as you can see, this more or less the thermoconductivity enhancement. In our case, if you remember, it was 33%, and what was measured by colleagues from the US and China and Korea and India, as you can see, these are the increases. But here, the one that we have has the world score, the world high increase ever measured. And that was, colleagues, in effect, the application is not in automotive engines. Any heat generating engine, the nanofluids can be applied. And the same thing also in Israel, for example, they are trying to use these nanofluids in CSP, in concentrated solar power, and the same also applies in Noor in Morocco. So instead to use standard water in the in the receiver, the idea is to use a nanofluid. So therefore, to transfer the maximum of heat from the solar absorber to the nanofluid inside the tube. The second one that I would like to share with you, colleagues, is how to use nanoparticles as a fertilizer. You have noticed, colleagues, that the cost of fertilizers is extremely very high. In particular, it has rocketed due to the fact that Russia and Ukraine are, in particular, Russia is a major nitrogen-based fertilizer producer and exporter. And here it is, we are really dealing with hunger here, with food. So I'd like to share with you a work which was, and a patent which was finalized by these 3 or 4 fellows, one from Botswana, the other one from DRC, the other one from Egypt, and the other one from South Africa. And how can I say, organic fertilizers are used to feed the soil, but the chemical fertilizers are a must for food for the plants. And these chemical fertilizers, unfortunately, with the war in Russia and the rocketing price of the fertilizers, both phosphate-based and so on, have obliged us to try to find a solution. And as you can see, colleagues, I will not go through this because the limitation of time. What is sure is that, colleagues, we do not, here is the consumption of per continent or per country or of the fertilizers. As you can see, Africa is in violet color here. It is increasing, but it's minute relatively to all other continents and countries. Why? Because it's extremely expensive, and therefore it is now up to us to produce locally, no more buying overseas. And that's what we decided here in South Africa, to come and produce our fertilizers here in South Africa. And in effect, once the patent comes out, I would share with you, hopefully, and you will be able to do it in Algeria. In effect, subhanAllah, you will be doing it in your kitchen, in effect. And this is a moral obligation of us to share with you that knowledge. Colleagues, I will not go through the rest, or that the fertilizers market will be moving ahead and it will increase extensively. And I would like just to mention that it is a necessity for us to produce our nanofertilizers in Africa and no more counting on Monsanto or X, Y, and Z, but to do it ourselves. Enough is enough. Errare umano, perseverare è diabolico. So here, the case of calcium carbonate, colleagues, that we have produced, it's nanometric. It's not like the one that you buy from the guy, from, how can I say, in a form of big particles. Now, here is a nanometric, and it's a nanotubular calcium carbonate. It does not enter in the nitrogen family, nor in the phosphate family, but in the potash family. And the potash family, we can come with the solution, and we cannot anymore, we should not anymore buy from Monsanto or any other external supplier. Here is a typical, colleagues, tomato plant. This one is the control, and this one, the ones who have been fed in the same time, as you can see, colleagues, in the same time, the same day, by this calcium carbonate fertilizer. And you can see, colleagues, here the one that is the control given by the control plant, and here are those who are given by those who have been fed by how can I say, by the calcium carbonate nanoscale that we have formed, and the taste is the same. And colleagues, just to mention in effect that it is a must that we should produce our nanofertilizers locally, in particular for those who are based in the rural areas. And the methodology, colleagues, once the patent will come out, the methodology is really simple. You can do it in your kitchen. The second case that I would like to share with you, colleagues, is the air conditioning, the devising materials for air conditioning. Again, colleagues, here in this work, I would like just to mention that it was done, carried out by a PhD student and a postdoc student, a PhD student from South Africa, a postdoc from Sudan, and an emerging young scientist from South Africa, as well as another one from South Africa. And this is related to SDG 7, affordable and clean energy, to minimize the usage of energy from the grid in particular. And colleagues, again, and come back to the Enquist diagram, whereby we have air conditioning and insulation improvements are technologies which are of a special interest to minimize the, how can I say, to minimize the CO2 footprint. Just to set the scene, colleagues, is that here is a thermography of a house and the thermography of a car. As you can see, the heat loss or the heat gained is mainly through the windows. So we need to come with a coating, which would stop or allow us to stop heat to come in and stop heat to come to regulate the heat from the sun. That's the point. And as you can see, as you can witness, colleagues, is that in the future, mainly it's the glass industry who will be the driving force for the buildings. And therefore, when you speak about glass, we speak about air conditioning. Air conditioning, you need to have smart windows. That means windows coated with a material. And here, what we use a coating which is a very, very intelligent material. It has a specific phase transition properties, that is a vanadium dioxide at low temperature, below 60 degrees, below 68 degrees. It is insulator. It's a semiconductor, sorry. And above that temperature, it is metallic. What does it mean? Below this temperature, in this range, at low temperature, is infrared transparent. And above this temperature, it's infrared blocking. And therefore, you can use it as a smart coating to stop heat from the sun. So therefore, if you coat a glass, with this material, when the temperature is hot outside, it's cold outside, the heat from the sun is transmitted to the through the window. When it is hot outside, the heat from the sun is blocked. And therefore, as you can see, colleagues, here is if you do such a coating on a glass window, therefore you would regulate the heat from the sun. When it is cold, the heat comes in. When it is hot, the heat comes out, is blocked. And here, colleagues, two toy houses with the windows, one without any coating and the other one with the coating of a VO2. And here, colleagues, you have a thermometer, and both of them are flashed with the heat, with a lamp which simulates the sun. The one without coating, it's 42 degrees Celsius. The one with the coating, it's 32 degrees Celsius, colleagues. And then nearly, how can I say, nearly 9-10 degrees between. And colleagues, and you would do understand that this is a smart window if you use this. Colleagues, you would understand that these smart windows would be a major component when it comes to air conditioning in buildings and in cars. And certainly, by opposite to air conditioning, it does not consume energy because this material is smart. It does not consume any energy. Colleagues, because due to limitation of time, I have just 2 minutes. I have maybe to just really to share with you this this case, and I think I would have to stop. Allow me just, please, dear chair, to share this one. Okay.
Okay, go ahead.
Thank you. This one, colleagues, is a work which was done involving this fellow from Senegal, this fellow from South Africa, this fellow from Egypt, this one and this one from Iran, and the three of them from Iran. It has involved high computational staff, chemistry expert, an engineering expert, a chemistry expert, and a material expert, and a modeling one. In this case, colleagues, as you can see, here it's related to water. Here, colleagues, is a graph showing more or less the water situation in Africa, and in particular sub-Sahara. As you can see, by 2025, you have to see not the cyan bars, but the dark bars. Nearly all countries will be under vulnerability level, nearly all of them. And some of them are under scarcity. So therefore, we have to treat the water. The water that we are consuming, we have to treat it. And for such, we have to design nanomaterials. Generally speaking, the material that is used as a photocatalyst to clean water is a TiO2. But the TiO2 has hiccups and has backups in a way that you have to use UV. And in our case, what we have done is that we have formulated the new form of TiO2, which is this one or that one. They are nearly black, and they are extremely active under infrared heat. And therefore, here, colleagues, just to show you, this is water contaminated with the methylene blue initially, and after a certain time, colleagues, when you shine without any light, just with the light of the tube and the water inside, it becomes transparent, and the methylene blue is decomposed. You know, colleagues, methylene, if you decompose methylene blue, you can decompose any insect pesticide. And in that regard, colleagues, here it's extremely very fast. Also, it's 2 hours time for the full decomposition. And yeah.
Yeah, I think we can.
Yes, thank you.
Yeah, we can stop with this very, very nice picture. I think that all these are your collaborators in the work that you shared. Is it right?
These were the students that we have trained.
Yeah.
Fast, and now they became, all of them became bosses, directors of centers, minister. She is a minister in Ethiopia and in Egypt. She's a vice chancellor. He's a deputy director. He is a director of center in Libya. She is a minister in Rwanda, and she is a vice chancellor. He is a vice chancellor in Ouagadougou, and so on.
So yeah, so you train like a very, very high level cohort of people. يعطيك الصحة على كل حال. يعطيك الصحة. So yeah, we got like a lot of questions. Like I try to resume because almost they are some questions that are actually the same. It's just they change a little bit. So because we don't have a lot of time, so I will take the most important ones and the ones that are also a little bit general. So I will give you some question about what you just presented and some like general question about nanotechnology and nanobiology. Sorry, nanotechnology and nanoscience. So the first question about is related to the nanofluids part. So they asked, how does oxidation affect the fuel efficiency for nanofluids?
Well, first of all, there is, how can I say, the nanofluids being oxides or metals, they will bind to the molecules of the fluid itself. And therefore, how can I say, they would not affect negatively the fluid. The major problem with these nanofluids is the stability of the nanoparticles within the nanofluid. But thermoconductivity's viewpoint, they are not. They contribute positively.
Yeah, and so just like a second question, what is the lifetime of the nanofluids because of that stability problem? So how long they can use?
It depends. For example, if you take nitrides, the nitrides, nanoparticles of nitrides are extremely very stable. If you take metals and carbides or others, you are obliged to use surfactant to ensure that these particles will not coalesce, because if they coalesce, they become big. If they become big, they will feel the gravitation, and if they feel the gravitation, they will settle down. So it depends, how can I say, if some of them, they do go for 6 months, others for 1 year, but others for some days.
Yeah, so it's very depend on what kind of nanofluids we are talking about. Yeah,
correct. What application?
Yeah,
if you take the case of nanofluids applied in the biomedical field, for example, for drug delivery, that is not a problem at all, because it's straight. It's a short lifetime. While in the heat engines and so on, it could be a problem. Knowing that with the heat in a heat engine, you have in addition to the standard stabilization of the colloids in the fluids itself, you have the Brownian motion due to the temperature, and that increases. So it depends on what type of system that you are working on.
Okay, great. So concerning the nanofertilizer, so the second part of your application, so how we can produce this nanofertilizer and how we apply them to the to the ground, actually, to the
Yes.
agriculture.
One, nanofertilizer is better than the Monsanto fertilizer. Why? Because it's nano. Because it's nano, it can enter the cell easily. It can enter the roots easily. It can propagate through the, how can I say, the system of nutrition system of the plant easily. And in effect, in some of the cases, we are just starting to carry out a deep investigation from the biological point of view, from plant toxicity aspect and so on. What is sure is that these nanofertilizers are, by their nature, diffuse easily within the plant, and in effect, it's just what I will do is that when the patent comes out and then when the publications comes out, I will send it to you, and please send it to all the fellows who would be interested by such. In effect, we, how can I say, we have initiated the CO2 Grande Africa initiative.
Mm-hmm. Mm-hmm.
Those who are interested, I would like, and this CO2 Grande Africa, it's an initiative, it's related to conversion of CO2 to calcium carbonate and using it as a nanofertilizer. And this initiative, whereby we convert the CO2 to calcium carbonate as a nanofertilizer, has a double advantage. First of all, through it we are minimizing the CO2 footprint. We are absorbing, we are contributing to absorb the CO2. Second, not to sequestrate it, or not to, no, it's to valorize it, is to take the CO2 and convert it to something of value. And here, one, how can I say, I would be delighted. I put here my email. Fellows are encouraged to contact me directly, so we could create a group in Algeria who would be involved with us in the CO2 Grande Africa initiative.
Inshallah. By the way, there's a lot of students in Algeria that they works actually in the field of nanofertilizers, the seeds optimization and all this stuff, and I'm sure that they will definitely contact you, because we just shared also your contact.
Yes.
And they are very interested about that.
Okay.
So coming to another application, or maybe if we stay in that nanofertilizer, so is there a shared strategy from African country to produce and use our own nanofertilizer? So that means, is there like shared, like?
No, there is none. There is none. In our case, within the accent, within the chair, we are initiating this CO2 Grande Africa, whereby I will be visiting different countries all over the African continent, one by one, un par un. Et je ferai les expériences devant eux, de telle sorte à ce qu'ils puissent reproduire ça. And the CO2 Grande Africa, Grande stands for green, I do not remember, neutralization. Anyway, what is sure is that this CO2 Grande Africa is an initiative of the UNESCO chair, and we will train fellows all over the African continent, and both the small SMEs and academia, to try to reproduce this stuff in their home countries.
Are they more safe than the conventional fertilizers?
Well, I saw the tomatoes. The tomato, we have eaten them. We have done the, how can I say, we have done the mineral, the the toxicity aspect and so on. So, well, by the way, the calcium carbonate is used as a fertilizer, but in our case, the methodology that we came with from our side is unbeatable. Rien, personne ne peut faire mieux. Parce que, simply said, we can do it at room temperature. We produce this at room temperature, the nanofertilizer, with zero energy input, with zero waste. Simply said, the calcium carbonate that we form is nanoscaled at room temperature, à température ambiante, avec zéro energy input.
Un problème du son, Faïz.
Oui, Monsieur Maaza, vous êtes avec nous?
Je pense c'est l'occasion, donc on a dépassé l'heure, donc si Faïz, tu peux clore la conférence.
Oui, d'accord. En tout cas, oui, j'allais remercier Monsieur Maaza et j'allais juste lui poser une dernière question à la khatash. Ouais, il y a des gens qui ont posé la question par rapport à est-ce que c'est faisable en Algérie, donc on allait juste lui poser la question, est-ce que, vu que c'est un Algérien, il connaît très très bien donc l'environnement algérien, est-ce que cette technologie peut être donc faisable aussi dans notre pays? Bon, Malik, ça sera, de toute façon, on va le revoir encore 2 fois. Et puis voilà, on lui reposera cette question. Aussi, il y a eu beaucoup de questions de la part donc des participants concernant d'autres applications à la wastewater management, water salinity, all this stuff, also solar energy. Je suis sûr et certain qu'il parlera de ça, Inch'Allah, dans une autre présentation. Il va parler beaucoup plus des applications. Et donc, voilà, on posera les questions qui seront spécifiques à d'autres applications, Inch'Allah, dans les prochaines webinaires, Inch'Allah, qu'il donnera. Donc, voilà.
Juste un mot, et je pense que il est de notre devoir d'aller vers la réflexion de créer ce groupe de travail, on l'appelle comme on veut, sur la technologie, sur la nanotechnologie.
Oui.
Pour fédérer tous les gens qui travaillent, et surtout les Algériens, avec le Prof Maaza, et donc qui peut les aider beaucoup plus techniquement et contribuer peut-être au développement de cette recherche scientifique dans le domaine de nanotechnologie en Algérie.
Oui, exactement. Surtout que vous avez vu, donc il est membre UNESCO de cette let's say workforce, donc task force, si on peut dire mieux. Et oui, je pense qu'il faut en profiter. Il faut en profiter. Donc voilà, donc on vous remercie beaucoup. On remerciera donc Monsieur Maaza par email, vu qu'il n'a pas pu se reconnecter. En tout cas, يعطيكم الصحة, Monsieur Mahiddin Jodi Tanik, يعطيك الصحة d'avoir fait le host. Et voilà, on se voit la semaine prochaine.
Salam alaikum.
Salam.